All right, so this video is going to be about taking a look at that motion that we started looking at last week, the motion of constant velocity, and really getting into the idea of graphing it. So we're going to take it step by step in terms of graphing and seeing what graphs can tell us about this type of motion and even other types. But the first thing that we're going to do is we're going to do a little scientific experiment, right? So this is a way for you to kind of explore the nature of science and how science is done. I mean, you're going to be responsible for teaching science to our budding scientists, right, in elementary and middle school. So you kind of need to have a hand at doing some science yourself. So here is an activity that is on pages 11 and 12 in the physical e-text. I think it's something like 15 and 16 in the e-text. I know there's a little page issue there. I think if you actually look at the screen, the page that shows up on the screen, and look at the page number that's on that, it's 11 and 12. But I think there may be an issue with how the e-text is telling you pages. So anyway, you're looking for something that says exploring, bouncing, and there's a B word there that I don't ever use in my classroom. It's just a little fun thing that I do. So you'll hear me refer to as orbs. So what you're going to do first is you're going to find a few orbs or one or two different orbs and start bouncing them. So why don't you pause the video and then for 5 minutes and set yourself a timer because you need 5 minutes and I want you to do this for 5 minutes. Start bouncing orbs and make as many observations as you can. So you need like a pencil and paper probably to write down your observations. So pause the video and take care of that for 5 minutes. All right, so since you're back, hopefully you made a lot of observations. You know, it could have been observations like the rebound height doesn't ever get to the same height as where you dropped it from. Bouncing it on different materials was different, right? Different orbs, if they were made of different things, like a tennis orb and a racket orb, don't bounce the same way. I hope no one was dropping bowling orbs because that would probably be a little dangerous. So, in any case, hopefully you have a whole list of observations there. Now you're going to go on and finish questions 2 through 5 on that first page. So, two being how would you define bounciness, right? So, if you had this quantity that you are looking for in an orb, right? Bounciness, how would you define it? Would it be the ability for it to rebound to a significant portion of its drop height? Would it be the ability to make a loud noise when it hits? You know, how would you define bounciness? And then you're looking at other of variables, other things, other factors that affect a ball's, an orb's bounciness, right? So that's what you're completing. So pause the video and complete questions 2 through 5. Okay, so on the next page, page 12, or again, the next page that's in there, we're going to be doing an actual experiment. So you've made observations, right? So that's the first part of our scientific method is that you've made these observations, you've come up with maybe some questions to wonder about, but you have a set of knowledge that you already have. So you're going to find one of those questions that you can create a testable hypothesis and investigate to find your answer. So to give you an example, right, if one of your observations was that different materials affected how an object bounced, then you may ask a question: which material has the best bounce? Right? Which material? If you're bouncing a certain orb, which material gives you the best bounce? Um, so you may have a hypothesis then that you're looking for very hard materials, right? So like carpet's obviously not going to be a very good bouncing material, but I don't know. You could have like a tabletop made out of wood. You could have tile floors. You could have an island that is made out of granite. You know, whatever you happen to have, and you may come up with a hypothesis of I think maybe this one might be the best one, and you're going to investigate it. So here's a quick conversation that we need to have about investigating variables, right? So if in that example we have the question of which material that an orb is dropped on produces the best bounce, then here is our variables that we're going to deal with. We need to have different materials to bounce it off of, and that's going to be our independent variable. Independent variable meaning that that's the variable that we're changing, that we're manipulating. And then we have our dependent variable, which is what we're looking at and to make a response to how we're changing it. So we're looking at the bounce of the orb, right? So Maybe our independent variable would be that we are looking at the materials, right? So the tabletop, the floor, the carpet, and the whatever. That's our independent variable. The dependent variable would be looking at the bounce height, right? So which one produces the better bounce height. Then we have something called control variables. Control variables. Control variables just means that these are things that we know probably affect the outcome of our experiment that we're not necessarily looking at. Like one of your observations, more than likely, was that if you dropped it from a higher height, then you're going to get a higher bounce. So we know that the higher bounce is going to be affected by other factors, specifically drop height. So what we control in our experiment with regards to material is always dropping it from the same height, right? Maybe we can get a ruler and we drop it from 12 inches every single time, right? That's a controlled variable. We also want to, you probably made an observation that the different orbs bounce differently, right? So that's going to be another control variable. We're going to use the same orb for every single one of them. All right, always use a ping pong orb or always use a golf orb or something like that. Okay, so that is a control variable. So you're going to perform your investigation and complete questions 6 and 7 on page 12. Okay, so this is going to be turned in on Brightspace. Okay, and this is going to be kind of like a you did it or you didn't. There's no real right answer to these questions. I just want to make sure that you've gone through the steps and you have completed the scientific experiment. We're probably going to have one of these every maybe not every week, but every other week maybe. We're going to continue to have these little scientific experiments that we do throughout the semester. Okay, so the next one that shows up in the book on page 13 is taking a look at a specific question. And it is talking about taking unequally weighted orbs and dropping them. And they specifically say a cork orb and a lead orb that are the same size, right, equally sized, and dropping it to see which one lands first. Okay, the hypothesis may be that the heavy one lands first. But that's what you're going to figure out. And so what you would do is you would hold them in your hands at the same height and you drop them at the same time. And what would be really nice is you can use your sense of hearing, because if you just hear up like that, one thump, then that means they hit the ground at the same time, or they hit the tabletop, whatever it is that you're dropping on. If you hear a right, then the thump thump, then that's going to be a that they didn't hit. You know, to figure out which one hit first. So question 2 on that page is about you logging, right? You're going to drop it 10 times or so, and you're going to log what happened. Did they hit the ground at the same time? Did the light one hit? Did the heavy one hit? That sort of thing. So take some time and investigate your question here, and then complete the questions 3 through 5. All right, so you've investigated this. So let's see what should have been the result. So I like this video. This video is one that I always love to show when I talk about this in my physics class. So this is a very large chamber. They're going to drop a feather and a bowling orb. Obviously, they're not similarly shaped, but we're going to drop a feather and a bowling orb. And we probably know what's going to happen, right? And they drop it in the air. And yeah, the feathers are definitely affected by the air. Okay, but if they were similarly shaped objects, then the air wouldn't really affect them the same way. But in the vacuum chamber, so this building is this huge vacuum chamber. So they pulled out all the air and then they dropped it. So air resistance is not a thing. And you can see that these two objects, which are very unequal in weight, are actually dropping at the same rate. So what you should have seen is if you dropped unequal things or unequal weighted things, then they should hit the ground at the same time. If they didn't, then there's more than likely some error that is in there because of your dropping mechanism. So maybe go back and if you were always dropping with the same hands, right, heavy and light in the same hands, try switching it up, right? Then drop it again and see if you get any different results. Anyway, so it doesn't matter what the weight is; they will hit the ground at the same time as long as air resistance is not a significant factor, which is why the activity asked you to find similarly shaped objects and also similarly sized objects. That way, air resistance is not going to be a significant factor. on either one of those. Okay, so now we're going to get into the actual motion for the actual content for today. If I can move me around. Okay. So we're going to take a look at position and velocity, specifically what positive and negative position and velocity look like. So here are the answers to last week's kind of intro to questions, or to graphing. So this was one thing that you looked at for practice on understanding your graphs. There was 3 pages, right? So they all had 3 graphs. You had to come up with a table and a story. That should read story, not store. And so these are the answers. So you can pause the video if you want to, go and take a look to see what you did and see if you matched up correctly. And if not, try to figure out why not. All right, so another activity that you did was taking a look at the toy car, right? The toy car going forward and backward, or right or left, I guess I should say. So if you're going to the right, I pulled this from someone who had already turned it in. So if you went to the right, then you saw a graph that looks like this. It had a nice trend line that went through it. If you went to the left, you saw a graph that looks like this. This person's particular data had a time of about 3.3 seconds to go 90 centimeters, because I didn't give you enough room to show you all the way to 100, and then about 3.34 centimeters to go all the way from 100 back down to 10, again about 90 centimeters. So similar times, right? Similar amounts of times for forward and backward. We have a difference in the way the graph is sloping, right? If it's going to the right, then it's going upwards on those numbers from the meter stick. If it's going to the left, it's going downward on those numbers for the meter stick. And then but they have the same slope, right? Because it's the same 90 centimeters over the same or similar amounts of time. So they have very much the same slope in magnitude. It's just they're going in different directions. So what we're finding is that the slope of the line can actually tell us how fast it's going, right? Because it's a position divided by a time. So the slope of the line can tell us how fast it's going. And the direction of the slope can actually tell us what direction it's going, right? If it's a positive slope, it's going to the right. If it's a negative slope, it's going to the left. So let's go a little bit further into this. Let's analyze this situation. So this is actually posted underneath the notes. So if you want to do this with me, you're more than welcome. But this is the dog's data. So it's basically just it's just a dog that's moving. So here's our dog. And it starts off at a position of 0. And we look at it for 7 seconds to see what it, always forget that I have this, what it's doing for 7 seconds. So we can see after the first second, it goes half a meter, then another half a meter, another half a meter. By the time it gets to 4 seconds, it's over at 2. But then take a look. It turns around and it goes to 1, then to 0, and then it goes to -1, right? So what does -1 mean? What does negative position mean? Well, in any time that we have a point that's labeled an origin, 0, starting point, whatever you want to call this, right? This is our starting location. And there's going to be 2 sides to that starting location, right? This is a positive side. This is a negative side. So a way that you can think about this is if this is really truly a dog, right? Maybe their owner is standing at the back door of their house and they throw something to go fetch, right? They throw a bone in the yard and he runs out 2 meters, grabs the bone and then runs back. And instead of stopping at the door, he goes inside the house, right? So this is a point that's just behind where he started. And so it's a negative position. Okay, let's see that again. So half a meter every second. Right? Each one of these images is 1 second's worth of time. And then he turns around, but now he's traveling a bigger distance each second to get back to, or to get to the -1 meter displacement. Another way that we can look at this is just using arrows, and you can see every arrow is worth a second. So the first 4 seconds, we're saying that we have this arrow that's somewhat short and marching to the right. And then afterwards, we have 3 seconds to get all the way back here. And so you can see those arrows are bigger, meaning that he was traveling faster. But he turned around, right? He turned around after 4 seconds and took 3 seconds to get back to his final location. So that's another way that we can take a look at this. So what we want to understand is what's going to happen with our graph when this occurs. So in order to graph these things, specifically, I want to graph velocity. We can graph position just fine, but I want to graph velocity. So we need to calculate it. Okay, and in calculating velocity, we need to know how much it went in terms of its change in position. We also need to know the time it took to do that. So to find a change in position, we have to take a look at 2 data points. And we have to say, okay, we went from 0 to 0.5 meters in position. So we'll take where we ended up and subtract where we were to figure out how far we went. So it's always a final minus an initial, and this is an easy calculation. Obviously, 0.5 meters minus 0 meters is 0.5 meters. And we can do it again here. So if we ended up at 1 and we left from 0.5, then we went to 0.5, right? 1 minus 0.5 gives us 0.5. Same thing here, right? 1.5 minus 1 gives us 0.5. Same thing here. 2 minus 1.5 gives us 0.5. Now, it's going to change, though, because the dog turned around and went backwards on the number line, right? So in this case, we would have a 1 minus a 2, right? A 1 minus a 2, and that's going to give us a negative 1 meter. So this is a change in position of negative 1. And it's different from these because the dog literally turned around and started going back the other way, right? Its change in position was 1 meter, but it was 1 meter in the opposite direction. And that is giving us some information here. Same thing's going to happen here. 0 minus 1 gives us a negative 1 meter, and then a negative 1 minus 0 gives us a negative 1 meter again. The times are going to be all the way down. They're going to be the same, right? It's just how much time to happen between each one of these labeled points. 1 minus 0 gives us 1 second. 2 seconds minus 1 second gives us 1 second. And then you can figure out that it's the same all the way down, right? I'm going to move myself a little bit. So the next thing is the velocity, right? From last week, we saw that the velocity was a change in position over time, delta x over delta t. So that means we take this column, 0.5, and divide it by 1 second. So 0.5 meters divided by 1 second gives us 0.5 meters per second. You can say, of course it does. You divide by 1. But what we need to focus on is the unit, right? So the unit of everything carries with it. So 0.5 meters divided by 1 second gives us 0.5 meters per second of velocity. Right? So the unit is important there. Same thing here. 0.5 meters divided by 1 second gives us 0.5 meters per second. Okay, and we can go the next two the same way. I mean, down here, the unit's going to be the exact same. It's just that we're going to end up with this negative, right? Negative 1 meter per second. Negative 1 meter divided by 1 second gives us a negative 1 meter per second. So that is our velocity. It's different from these, right? Because we know the dog turned around. Moving from E to F, the dog turned around. And our velocity is showing us that by telling us that it's a negative value. It's also saying that it's going faster, right? 0.5 meters per second versus 1 meter per second. So this is a faster velocity. And we saw that, right? The dog covered more distance in the same amount of time on its way back. Okay, and then it's going to be negative 1 meter per second going for the rest of these. Okay, pause the video if you need to make sure that you have all of that kind of good. We're going to start graphing. So the first graph that we're going to make is a position versus time graph. So all I'm going to do is I'm going to graph these points on a graph. So here's our position versus time graph. It's over our, each one of these blocks is going to be a second. Each one of these blocks is going to be a meter. So our points look like this, right? So we're going up half a meter every second, and then we're going to go down a meter every second until we get to a negative 1 in position. So here's our positive direction. Here's our moving to the right, and then he turns around and begins moving to the left. Okay, so having positive to the right and then negative to the left. And this was very much like the toy car, right, that you did last week. Okay, this is our moving to the right, this is our moving to the left. They're different because of how they're sloped. They're sloping upward, moving to the right, sloping downward, moving to the left. It's just that this one also went into a negative position. So if I let the toy car go further back or from 0, right, if I had you track it, then we'd end up in negative position. So it would be the same thing. All right, what about velocities? So velocities, our data points are half a meter per second and then a negative 1 meter per second. Now you'll notice, and this is getting too far above where this class needs to be, but you'll notice I put them in the middle of the seconds, right? Here's 0 seconds, here's 1 second. I put the data point in the middle. It's only because remember we had to take 2 data points and use those to figure out what the velocity was between the 2 data points. So this is more of like an interpolation kind of thing, but don't worry about it. So while it's moving forward, we have this positive 0.5 meter per second velocity. While it's moving backwards, we have a negative, right? Negative 1 meter per second velocity. But then you have this change that happens in the middle. And that change happening in the middle shows a positive velocity moving to a negative velocity, right? So what happens here at this second is that a positive velocity moved to a negative velocity, which means that the object turned around, right? That's all it means. The negative velocity just means that the object turned around. So I want to take a look at these together, right? When does the position become negative? Well, it doesn't become negative until, second 6, right? 6 to 7, it doesn't become negative. That's when the dog passed where he started and moved back the other way. When does the velocity become negative? Well, that happens at around second 4, right? It's 4 seconds to get out to the 2 meters of displacement, and then he turns around and goes back the other way. And so that happens for the last 3 seconds, it becomes negative. So negative velocity and negative position mean different things, and they're not tied to each other in any way. Right? You can have negative velocity along with positive position. It just means that you're on the right side of the zero still, but you're moving to the left. Okay, you can have negative position with negative velocity. That means you're on the left side of zero, and you're still moving to the left. Okay, you can have any combination between negative and positive position and velocity. That's what these graphs are trying to show us. So a summary here is, move me out of the way so you can see the word negative, is that if you have positive position, it just means that your location, and I wrote this very generally just because I'm a physics teacher and I have to, okay, position, if you have a positive position, it means that your location is on the positive side of some point that has been labeled 0. Okay, go back all the way to that slide that had the dog on it, right? So that there's a point that's labeled 0, and if you're on this side, then you're in positive position. Usually that means the right side. I say usually because it doesn't have to, and we don't always have to say it's right and left. We can say forward, backward, we can say up and down, right? It just depends on the motion of the object. So location is on the right. If you have a negative position, that just means that the location is on the left, or it's on the negative side of 0. Right? Just where you are. That's what's determining whether you have a positive or negative position, where you are. Your velocity is going to be tied to your direction of motion, right? Which way are you moving? Not where you are. It doesn't say location. It says the direction of your motion. Okay, is your direction of motion producing more positive position values? That's going to be, you have positive velocity. It's going to be moving to the right if you're in that same kind of system, right? Is your direction of motion moving towards more positive position values? Similarly, if you have a negative velocity, it means the direction of motion is moving you to more negative position values. Now, I'm not saying that you're going into negative position. I'm saying that if you're at 20 meters and you're going down to 19, 18, 17, 16, right, that's decreasing your position values. That's not making yourself more positive. That's trying to get you back to 0. So that is more negative position values. It's heading towards the negative direction. But similarly, you could be at -6 and go from -6 to -7 to -8 to -9. That's more negative position values, right? But that's still moving left. So you can have any combination between any of those position and velocity positive negatives because they mean something different. So going forward, you are going to be expected to need to calculate slope from graphs to figure out how fast something's going. So you can use this review video right here. That tells you how to calculate slope using your 2 points on a graph. You can also use this concept builder. This is linked in Brightspace, so I'm going to go and show it to you. So when you click on it, it's going to bring you to this website. So when you make this full screen and you can hit start, then it's going to give you some levels here. And this is just practice. I'm not asking you to do it. If you're good at calculating slope, that's completely fine. So in this particular case, it says, hey, you have this position versus time graph. If you went 15 meters in 25 seconds, then you would do that calculation, right? 15 divided by 25 and put that slope right here. The other thing that you can practice is what happens if it doesn't start from 0, right? What happens if it starts from some higher point? How would you figure it out then? And then this one is if you have a negative slope, what happens if it's going down? So try them out and figure out if you know how to calculate slope in all those situations. Come back to our notes. The last thing is getting at the question that was in the toy car exercise that you did, and that is, what do you think the graph would look like if you were speeding up or slowing down, right? So two things that we need to remember is that on a position versus time graph, the slope of that line represents the velocity of the object. So if it's a steep slope, that means it's going fast. If it's a it's not skinny, little slope, I don't know, sorry, then it's going slowly. If it's flat, that means it's not moving at all, right? It has a velocity of 0. It means it's staying at the same position the entire time. So like these last 3 dots over here, I made it so that it's at the same position no matter what time it is, so the object has stopped, right? Shallower, that's what I was looking for. Shallower slope. Steep slope, shallow, right? And then a changing velocity would mean that the slope of the line would change. So in this case, this is an object that's slowing down because it starts off steep and it gets shallow over time, right? The lines that you can see that are drawn between data points are getting steep to shallow and eventually gets to flat to horizontal. And so that means an object is slowing down, right? This graph would mean slowing down whether if it was negative position or not, right? So if it was negative position, that same graph, if it was going like this, it would still mean slowing down. Being in negative positive position doesn't mean anything when it comes to velocity. So I'm going to leave it to you to think what would look like if the object was speeding up, right? What happens if it has shallow or zero slope at the beginning and then it gets to something steep over here? What would that look like? Try to draw it out. Okay, so the last part of the video, I'm going to just run through what it is that you're doing this week. Let me see. I thought I had it open. Well, so I'll just explain it to you. So you've got a few things, right? You've got your exploring orbs activity that you did, right? There is a discussion question that you're going to do that involves what we call an assessment probe. That's just what we use in school to get some formative feedback. So it's a discussion question. Basically, you're going to open it up. It's going to be a PDF. It's going to be some people talking about a graph. You have to decide who you want to agree with, and you have to explain why. There's some instructions there, though, about agreeing with people. So there's a discussion question. And then what I'm going to do this week, and probably for here on out, just the end of the module to test your learning, there are what I'm calling review questions for the module. So there's 10 questions. You have 2 attempts. So if you go through the questions the first time and read any feedback on some of the questions, not all the questions have feedback, but a lot of them do, the harder ones do. So after you go through them, if you want to ask questions, you can ask questions, but then you can go back and do a second attempt, and the highest of the 2 attempts is what we're going to take for a grade. So that is what we're doing for the week. As always, email me if you have any questions, and you guys have a great week.